All right, cool. Let's get started here. So we've got a new unit to kick off, and this particular unit is going to be focused around chemical reactions. After all, this is a chemistry class, so we should talk about actual chemistry here at some point. Up until this point, we've kind of been laying the groundwork, building the various tools in our toolbox so we can accurately talk about chemical reactions. All right, first place we're going to start is something that we kind of introduced previously, but we need to go a little bit more in depth into, and that was what we called our chemical equations. All right, so a chemical equation would be something like nitrogen plus fluorine gives us NF3, nitrogen trifluoride. All right, so the basics of what we learned about our chemical equation thus far is we learned that everything on the left side of the arrow we call what? Our reactants. And everything on the right side of the arrow we call products. All right, and important terminology in a chemical reaction, your reactants get consumed, right? They're getting used up as this chemical reaction is occurring, and your products get produced. Cool. So what was the first thing we learned we have to do when we get a chemical equation? Balance it. All right, cool. So every time, very first step is going to be to balance your chemical equation. Everybody take a second and balance this chemical equation for me. Okay, so remember when we're balancing, we're making sure we have the same number of nitrogens on both sides, the same number of fluorines on both sides. So I'm keeping a track of the total of nitrogen on each side. And I can see I have this imbalance in my number of nitrogens. Remember, you're not allowed to change the chemical formula, but what you can do is update these coefficients out front of your chemical formula. So if I put a 2 there, now I have 2 nitrogen trifluorides. Okay, so those are balanced. But I also got to update the number of fluorines I have on my product side. Each one of those has 3 fluorines, so now I got a total of 6. So my nitrogens are balanced, but my fluorines aren't. I can balance that with a 3 out front there. So now I have 6 of each. Okay? Cool, so this would have been a review of what we learned. This chemical equation is still not done yet. We still don't have a pretty perfect chemical equation. What's missing is what's called the states of matter of these compounds. Okay, so next to nitrogen gas, if we were being good in our chemical equation, there would be this little G here. Same thing with fluorine and nitrogen trifluoride. They all have this little G next to them. What do we think the G represents? Gases. They're gases. Okay, so by states of matter, I mean we can have an S for solids, an L for liquids, and a G for gases. Okay, I make my L kind of that fancy cursive L just so I don't think it's a 1, but that is in no way, shape, or form required. Okay, the last state of matter that we'll see a lot, and we'll talk about this even more in depth when we introduce solutions, is this AQ designation here. And this means an aqueous solution. Aqueous is just a fancy way of saying water-based. Okay? So in our chemical equations, we have our formulas of our reactants, our formulas of our products. A chemical equation is balanced or else it's worthless to us. And we have to include the states of matter of our compounds. Cool. All right, so the first thing we want to be able to do is take a description of a chemical reaction. So for example, sodium reacts with oxygen. To form sodium oxide, solid sodium oxide. And we want to take this and turn it into a balanced chemical equation here. Okay, so first of all, what are our reactants in this reaction here? Sodium. So that's a reactant. What's another reactant? Sodium reacts with oxygen, so that's another one of my reactants. Okay, and then what's my product here? That's sodium oxide. So I need the symbol for sodium and oxygen on my reactant side and the symbol for the sodium oxide on my product side. Did I say that right? Symbol for sodium and oxygen on the reactant side, sodium oxide on the product side. Okay. What's our chemical symbol for sodium? Na. But again, now we have to include these states of matter here. All right, so how can we tell the states of matter of our elements in what are called their standard states when they're all by themselves? For that, we're going to look up at our periodic table that we have up on the board here. We see we have all these different colors up here on our periodic table. Most of the elements, these symbols are given in black. We have a few that are given in red. There are actually only 2 up there that are in blue. And then we have some in white. All right, so that corresponds to the state of matter of that element when it's in its pure form, when it's all by itself. Okay, so our solids are going to be the ones, well, so let's just see if we can guess. Iron and copper and silver, they're all in black here. So what do we think the black corresponds to? Solids. All right, cool. So these are the ones that are represented in black on our period. Let's actually put this in a separate place. We want to be clear that we're talking about elements in their standard states. Okay. And again, standard state is just a fancy way of saying all by themselves. So sodium, when it's all by itself, again, it's in black on our periodic table, so that gets this S designation. So the elements that are listed in black, those are solids in their standard state. Okay? If we look this very last column on our periodic table, all the way on the right-hand side, what do we call those elements in that column? Noble gases, and they're all listed in red here. So what do we think the red represents? Gases. Okay? There are only 2 elements that are up there that are listed in blue. Can anybody find one of them? Mercury is one of them. What's the other one? Bromine. So these are the only two elements that in their standard state are liquids. Okay, and then lastly, we have a few of them that are listed in white here. These are the man-made elements. So we don't really know what their standard state is. They don't exist. You don't dig them up out of the ground. Somebody made these atoms in a lab somewhere and said, yep, you can make it, and they put their name in the record book, and that's the extent to which they exist. Okay? So these white ones are what we call the man-made elements. And for those, you basically don't have to worry about it.
So none of those are naturally occurring?
Correct. Most of them are the largest one. The really bizarre one is 43, technetium. Okay, kind of sitting in the middle of the periodic table. Nonetheless, there are no elements with 43 protons here on Earth. Only exist in the lab. Okay, so we got our formula for sodium, and we said that this is going to react with oxygen. Okay. Now, I think maybe from like biology class or whatever, we all know the formula for oxygen is what? It's not just O all by itself. O2, okay? So oxygen is O2, and then let's just finish this off here. What should I put for my state symbol? G, for a gas, right? Because it's listed in red. Okay, so we have our state symbol for our elements. The other thing we have to consider are that some elements are what are called diatomic elements. Our diatomic elements are elements that are always found in pairs. So there's no such thing as a single oxygen atom floating around all by itself. There are always two oxygens bound to one another. When you say oxygen, everybody knows you're talking about O2 because oxygen is one of these diatomic elements. So these are elements always found in pairs. Okay, so we just got to know what these elements are. All right, there are 7 diatomic elements, and conveniently they form a little 7 on the periodic table. So nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are all diatomic elements. You never just have a single fluorine atom floating around all by itself. They're always found in pairs. So just like the formula for oxygen is O2, the formula for fluorine is F2. Okay? But I said that there were 7, and I only put a box around 6 here. The last one is always kind of on the wrong side of the periodic table. Hydrogen is also a diatomic element. So these are our 7 diatomic elements. When I say hydrogen, I don't just mean one atom of hydrogen, I mean the pair, the molecule H2. Okay, so I think it's helpful to visualize it on the periodic table, helps you keep track of who's who, but we can just make a definitive list for our notes here of these 7 diatomic elements, again, in order of increasing size. Yeah, H2, N2, O2, and then the halogens, fluorine, chlorine, bromine, and iodine. All right, cool. So now we have our reactants. We got to get our product here. How am I supposed to know what sodium oxide is? Well, now we got to rewind back to what we learned how to do in the first unit, right? We learned how to name all these things so that we could use them going forward. And when I'm putting this formula together, it's all about the charges. So sodium has that +1 charge. Oxygen, oxide, has that -2 charge. So when I do my swap, I get Na2O. And then to finish this off, what's going to be the state of matter of that sodium oxide? Solid. How do we know that? because it's given in the problem, right? You can't just look at the periodic table and tell what every sodium compound is going to be. It doesn't work like that. So for these compounds, you'd have to be told what they are. I will tell you, ionic compounds are always solids at room temperature, but that's not the case for every compound, right? So that information has to be given to us. It's only elements in their standard state that we can tell from the periodic table. So again, in the problem, it tells me that this is solid sodium oxide. And then we're done? No, why not? Balance it. This thing, we're going to see today why this is worthless unless it is a balanced chemical equation. So everybody take a second and just finish and balance this chemical equation. Okay, so just to kind of do this the long way so we can see, let's say I'm going to balance my sodiums because that's the first discrepancy I see. Then I get to my oxygens and now I got to balance that. Oh, that didn't work. So now my oxygens are balanced, but I got to update those sodiums. So now I got to jump back in order to fully balance my chemical equation here. All right, again, guess and check. Sometimes you might update and have to go back. That's perfectly fine. What's up?
So ionic compounds are always solid at room temperature?
You would be told, but yes, they are. But nonetheless, we don't have to even file that away here. You will be told what the state of matter is for these compounds. Again, you're not expected to know what every compound is. But elements in their standard state, when they're all by themselves, we can tell by looking at the periodic table. Cool. All right, let's do one more here from scratch. You guys are going to write a balanced chemical equation for the following reaction. All right, we're going to take liquid sulfur hexafluoride. This decomposes into fluorine and sulfur. All right, so write me this balanced chemical equation for this reaction here. All right, so what is my reactant? Sulfur hexafluoride, so that's SF6. And what's the state of matter? liquid, again, because it's told to me. So this is going to decompose or break apart into fluorine. What do I have to do to finish off the formula for fluorine here? F2, that's one of our diatomic elements, and fluorine is a gas. It's in red up on our periodic table. As well as sulfur. Is sulfur one of our diatomic elements? No. What is the state of matter of sulfur? Solid. Okay, and then lastly, I have to balance this. This one's not too bad. My fluorines are just imbalanced, so I'll have to put a 3 out front of the fluorine on the product side. What's up?
So is it always on the left side, is always reactants regardless of the chemical equation, or?
Yes.
Okay, so
Yes.
it doesn't matter if it's just left side and right side?
Yeah.
Okay.
There will be a time when you talk about reactions going in both directions, but that is not even this course. That'll be a future semester, so don't you worry about that. Yes, reactants are always listed on the left, products are always listed
So
on the
it's
right.
not the plus that, okay, because I was thinking that plus was the reactant indicator.
No. And I guess also to be clear, you don't have to put your products in a specific order or your reactants in a specific order. You could have written this exact same chemical equation. You do have to have the reactant as the sulfur hexafluoride. But if you swapped sulfur and fluorine on the product side, this is the exact same chemical reaction. There's no like, well, if this will work. There's no right, this is equivalent. Okay? Just like how in math class, A plus B is the same thing as B plus A, that's the same with our chemical equations. Okay. All right, and then how did you know that sulfur hexafluoride decomposes into fluorine and sulfur? You don't. I told you, right? I mean, you don't have to know every chemical reaction that exists. Y'all don't know any chemical reactions at this point, or at least I'm assuming you don't. That's how the course is structured. We'll learn about certain chemical reactions. There will be certain categories where you will be expected to tell me whether or not this reaction occurs, but we're not even there yet, right? No chemist knows every chemical reaction that occurs in the world. It doesn't really work like that. Usually you study your one little segment of the world and you become an expert at it. But the bottom line is you're not expected to know this reaction occurs. I told you this reaction. You are expected to interpret that into a chemical equation. Okay? And again, there will be certain categories of reactions that we study in-depthly, and you'll be able to predict the products for, but we're not quite there yet. And that will segue us into these various categories of chemical reactions. Okay, so given a chemical equation, we want to be able to place it into one of these categories here. All right, so the first one are what are called synthesis reactions, also called combination reactions. Okay. A synthesis reaction is where we have multiple reactants combining into a single product. Okay, and then the flip side of this are what are called decomposition reactions. These are reactions where you have a single reactant decomposing or breaking up into multiple products. All right, so I want you to look back at those previous two chemical equations that we wrote from the description of the reaction. And I want you to categorize it according to whether it's a synthesis or decomposition reaction. All right, so this last one that we did, which category would this fall into? Our sulfur hexafluoride example. Yeah, so we start out with just one reactant, and it breaks apart, it decomposes, we got a little keyword here, into these multiple products here. So absolutely, this is a D. Let's just put that as an example. All right. And what about the one with the sodium oxide? This would be a synthesis reaction. We have multiple reactants, our sodium and our oxygen, and they're coming together to form that one product, that sodium oxide. So this would be an example of a synthesis reaction. Okay, so the next two are a little bit harder to spot pattern-wise, so I'm going to use some colors here. We have what are called single replacement reactions. All right, and these all follow the same basic formula where you have something all by itself. I'm going to call it A. And it's reacting with this compound BC, right? An ionic compound where B is my cation and C is my anion. And what we're going to see in our single replacement reactions is that A and B swap places. So all of a sudden B is all by itself and A is paired up with C. All right, so an example that you guys did last week in the lab. You took solid zinc and you put it in a solution of copper sulfate. That copper sulfate was that blue solution, and it started to bubble, and all of a sudden that blue color disappeared and a bunch of copper precipitated out. Right? So your solid zinc got consumed in this reaction, and we got solid copper. Where did that zinc go? It became aqueous zinc sulfate. Okay, and so just to sort of follow our colors here, if I said that zinc was A, copper was B, and my sulfate was C, we can see that zinc and copper swap places, so now the zinc is paired up with that sulfate ion. Okay, So these are these single replacement reactions. We'll talk about them a little bit, and then they actually play kind of an outsized role in the second semester, talking about electrochemistry, because these are reactions where electrons are exchanged, and so you can use these reactions to power batteries. But we'll get there, okay? Next, we got double displacement. All right, again, we're going to kind of illustrate these with some colors here. We start out with two compounds, AB. And CD. And again, what's going to happen is we're going to swap places. This time we're going to switch the A and the C. So now we're going to have A paired with D. And what am I going to pair C with? With B. Okay, so not dissimilar to what we saw before. Swap, it's just now it's not A all by itself, it's two compounds. But again, we're going to swap to get our product. Okay, this particular category we'll study quite a bit going on here next week, because there's a specific category called precipitation reactions. So an example is if you take a solution of sodium chloride and silver nitrate. Again, what does that AQ mean? Aqueous. So to be clear, that means I took sodium chloride and dissolved it in water. A lot of reactions are carried out in solution, in aqueous solutions. Solids don't really react with one another. There's not much movements of the atoms between two solids. That's not to say it never happens, but it's just more rare. If you do take that and dissolve it in solution, these things are able to freely float around and react with one another. I was a biochemist. Literally every reaction I ever did in my research was in solution. All right, and we'll talk a little bit more about this in depth, but just to give you a preview of where we're going. Okay, so now I'm going to swap my sodium and my silver, right? Sodium's A, chloride's B, getting my colors straight, silver and nitrate. So now I'm going to swap and put my sodium with the nitrate, and my silver goes with the chloride. Okay, and again, for right now, you're just going to trust me that this reaction happens, and again, we'll study it in a little bit more depth, and you'll be able to predict whether or not this reaction happens, but we're not there yet. Cool. All right, so our last category is what we call combustion reactions. A combustion reaction is where you react a hydrocarbon. All right, that's a scary word. Let's think about what I mean by hydrocarbon. What two elements do we think are in a hydrocarbon? Hydrogen and carbon. All right, so that's anything with this formula CXHY. Remember, for covalent compounds, we can't predict what it's going to be. They could be anything. So these react with oxygen to produce carbon dioxide and water vapor. Okay. So let's look at an example of a combustion reaction. Okay, so C5H12, that's going to be my hydrocarbon. This is pentane, it's a liquid. And what am I going to react this with? Oxygen. And so what's the formula? O2, gas. This is going to make CO2, which is what? Carbon dioxide. And is that a solid, a liquid, or a gas? That's a gas. Okay, that one I do expect you to know. All right, and water vapor. So importantly, not liquid water, but gaseous water. Okay. These reactions, the reason why it's gaseous water, these reactions generate a ton of energy. So the water that's produced is in the gas phase, not the liquid phase. Okay. For these here, I want you to balance this, but let me just remind sort of strategy-wise here. This particular chemical equation, we see one element all over the place, oxygen. It's in both of our products. That's going to make balancing the oxygens kind of a pain in the butt. So your strategy is to save oxygen for last. Balance your carbons first, then your hydrogens, then at the end go back and balance your oxygens. Okay, so if I balance my carbons, I need to put a 5 on the product side outside of that CO2. If I balance my waters, each water already contains 2 hydrogens, so I would put a 6. So now if I worry about my oxygens, I have a total of 10 plus 6, or 16. All right, so then how can I square that away on my reactant side? Put an 8. Okay. Other things to note about this combustion reaction here. Again, these are reactions that release a ton of energy. And it really is kind of a ridiculous amount of energy. Like per gram of hydrocarbon, there are very few chemical reactions that release quite as much energy. Okay? We humans have then got addicted to using this particular chemical reaction to power the world around us. Keep on the lights. Your car, unless you drive a battery-powered car, what the hell are they called? An EV. All right, you have a combustion engine. What your engine is doing is when you fill up your gas tank, you're filling it up with a bunch of hydrocarbons. And what's happening inside of that engine is it's reacting with oxygen gas to produce carbon dioxide and water vapor. And that's what's powering your car down the road. Okay? So we humans, we dig up these hydrocarbons, we combust them, and we take that energy and we use it to power the world around us. The problem is that one of the byproducts in this reaction is carbon dioxide, right? So over the past 100 years, all we've been doing is dumping a ton of carbon dioxide into the atmosphere, and the planet's a little pissed off about it, all right? So that's something you would talk about climate change in your industrial science class, not industrial, your environmental science classes. But this particular reaction right here is exactly why we have this climate crisis, okay? So this reaction releases a ton of energy, and we use that to power the world around us. The other thing about this reaction that's probably even more important for y'all is that this is our first reaction where you should be able to predict the products. right? Given a hydrocarbon and being told that it's a combustion reaction, you should be able to write me a balanced chemical equation. That's because that hydrocarbon is always reacting with oxygen and always producing the same two products, carbon dioxide and water. Okay, so let's practice this real quick. You're going to write a chemical equation for the combustion of gaseous methane. And methane's formula is CH4. So I'm going to start out with my CH4. My problem told me this was a gas. And what's my other reactant? O2. And again, that's because it's always O2 for a combustion reaction, right? There's the key word in our problem. I told you it's a combustion reaction. And in a combustion reaction, you always have the same two products, carbon dioxide and water vapor. All right, again, to balance these, you want to save the oxygens for last. My carbons are already balanced. To balance my hydrogens, I need to put a 2 out front. Now if I look, this will give me a total of 4 oxygens on the product side. So 2 over here will balance everything out. Okay, so in the previous examples that we did, when we were turning this sort of description of a reaction into a chemical formula, you were told what the reactants and the products were, right? Sodium reacts with oxygen to form solid sodium oxide. For a combustion reaction, you should be able to do this one just from a description, being told it's a combustion reaction and given that hydrocarbon formula, because it's always the same reactants, your hydrocarbon and oxygen, combining to form carbon dioxide and water. The balancing, you can compare the two and see that the balancing changes depending on the formula for the hydrocarbon, how many hydrogens and carbons there are, but the reactants and the products remain the same. Okay, cool. So we made a big stink about balancing our chemical equations, right? So why do we bother balancing our chemical equations? They're not very useful to us unless they're balanced. And what we're going to build towards here is what's called a stoichiometric ratio. Okay, so let's just take an example reaction. We're going to do that first combustion reaction that we talked about. That C5H12 plus 8 O2s give me 5 CO2s and 6 waters. Okay, this is that first combustion reaction that we talked about. Okay. So importantly, what this chemical reaction is saying, or one thing, it's actually saying quite a lot, but one thing I can say quantitatively that this chemical reaction is saying, oops, that didn't work. Is that if 1 mole of C5H12 is it going to be consumed or produced in our reaction? Consumed. How do I know it's going to be consumed? Because it's on the reactant side. Reactants get consumed, products get produced. So if 1 mole of C5H12 is consumed, then how many moles of CO2 are produced? And how'd you get that? Straight from the balanced chemical equation, right? Our coefficient from our balanced chemical equation says that if 1 mole of that C5H12 is consumed, I'm going to get 5 moles of carbon dioxide. Okay? So we can turn this into what we call a stoichiometric ratio, where I build one of those quantities over the other. So 1 mole of C5H12 consumed over 5 moles of 5 moles of CO2 that are produced. But I could pick any 2 compounds in my chemical equation and do sort of the same game. All right, so I want you to build me a stoichiometric ratio for moles of O2 consumed over moles of H2O produced. Okay, so if 8 moles of oxygen are consumed, again, I get this straight from my balanced chemical equation. That coefficient out front is an 8. How many moles of water are going to be produced? 6. And again, you get this just from your balanced chemical equation. Now, I picked something from one side and something for the other. This balanced chemical equation locks in these ratios in which your reactants are consumed and your products are produced. You don't have to pick stuff from this opposite sides. I could likewise build a stoichiometric ratio that said, all right, if how many moles of that C5H12 are consumed, well then great. How many moles of O2 are consumed along with it?
Why don't we have to reduce?
Mathematically you could, but there's no point to, and it's easier to see where it came from if you don't. And we'll talk about how we use this in a math here in a second. Okay, so if 1 mole of that C5H12 is consumed, how many moles of oxygen are going to be consumed as well? 8. Again, just straight from my balanced chemical equation, from the coefficients in my balanced chemical equation. So these are what we call our stoichiometric ratios. And they come from your balanced chemical equation. All right, cool. So, chemists are lazy, like all scientists, all right? Because, how did I know that my oxygen and my C5H12 were consumed? Because they were on the reactant side. How did I know that water and CO2 were produced? They were on the product side. So, when we do our stoichiometric ratios, it's overkill to write the words consumed and produced. So really what you will see for a stoichiometric ratio is just from your balanced chemical equation, the coefficient moles of C5H12 over moles of CO2. We know what's being consumed from our balanced chemical equation. We know what's being produced from our balanced chemical equation. Okay? Now, hopefully everybody looks at this and says, this stoichiometric ratio, again, that's what we call these things, reminds me of something that we've used a bunch in this course thus far. We got one set of units on top, another set of units on the bottom. This looks a lot like the conversion factors that we've been using to convert from, say, inches to centimeters. This is what these stoichiometric ratios are going to do. If I know how much pentane has been consumed, it'll allow me to calculate how much of my products have been produced. All right, so our stoichiometric ratios, these are going to be conversion factors. We get to use in our math. Okay, so importantly, every one of our stoichiometric ratios we can use as is, or we can flip it, just like every other one of our conversion factors. All right, and which one we're going to use is going to depend on our problem. It's going to depend on our math. Right? We're going to pay careful attention to our units. Now, looking at this carefully, if I said 1 mole of C5H12 was consumed, how many moles of water were produced? What would you say? 6. So that's easy enough, okay? But what if I said if 0.369 moles of C5H12 are consumed, how many moles of H2O are produced? Now you're going to have to do some math, right? And this is where we will use our stoichiometric ratios. All right, let me get rid of my markings here. Okay. So we have our balanced chemical equation. We have our problem here. Okay. Step one, we need to build those conversion factors. Again, we got a fancy name for it, stoichiometric ratio. Okay, so I got a bunch of different stoichiometric ratios I could build from this one chemical equation. Let's look at which one I'm going to actually need. My problem is telling me that I'm starting out with my C5H12, and it's asking me how many moles of water are produced. All right, so these are the two compounds that we want to build our stoichiometric ratio for. I want a stoichiometric ratio for moles C5H12 over moles H2O. All right, everybody take a second from our balanced chemical equation. Give me that stoichiometric ratio. So that's a 1:6 ratio. And again, I can always take that or flip it upside down. All right, and then we're going to move on to the calculation step. I'm going to start with my quantity that's given. And here is where keeping track of who you're talking about is going to be really helpful. I don't just want to say moles of, I don't want to just say moles, I want to say moles of C5H12. We got a lot of compounds floating around here. We got to keep track of who we're talking about. Okay, I'm going to multiply this by one of those stoichiometric ratios that we just built. Which one do I want to use? The one on the left or the one on the right? Right. And why the one on the right? Because I need moles of C5H12 on the bottom, so it cancels out. And moles of H2O on the top, so that's what I'm left with when I look at my units. All right, and again, we said that was a 6-to-1 ratio. Cool. All right, so we punch this into our calculator. We get 2.214. What are my units? Yeah, so I canceled out my moles of C5H12. I'm left with moles. That is your unit, but again, it's very helpful to keep track of who you're talking about. And then I'm done. No, never that simple in chemistry. What's that last step we got to do? Sig figs. Okay. How many sig figs are there in my initial measurement? 3. All right. Stoichiometric ratios are always exact. It's going to be exactly 6 moles of oxygen produced for every 1 mole of our hydrocarbon here. So that means I need to round my final answer to 3 sig figs, or 2.21 moles. Yeah, we can keep track. Boom. Okay, so these stoichiometric ratios, we get them straight from our balanced chemical equation. It's real. Once you balance it, that's the hard part, right? And then you just take those coefficients, stack them on top of each other. But importantly, this is how we do math with a chemical reaction. All right, let's try one from scratch here. I'm going to give you a chemical equation, and you're going to balance it for me, and then you're going to use that balanced chemical equation to solve this problem here. Alright, let's do. Okay, so you're going to balance this chemical equation, and you're going to use that balanced chemical equation to tell me that if 2.7 moles of this iron 3 chloride are produced, how many moles of chlorine must have been consumed? Alright, in terms of balancing, this one was a little bit of a pain. My irons are balanced, but I got a 2 on my chlorines on the reactants and a 3 on my products. And I can't turn a 2 into a 3, so instead I got to turn them both into 6. They're least common multiples. So I'm going to put a 2 out front, my product side. Now I got 6. And a 3 on my reactant side. I just got to update my irons as well, so I don't need a 2. Cool. Alright, so now that I have a balanced chemical equation, I'm going to look at my problem. I need a stoichiometric ratio that's going to allow me to jump from moles of iron 3 chloride to moles of chlorine, right? So looking at my balanced chemical equation, that'd be this one here and this one here. Alright, and again, that's kind of what you want to think about. Is you know this one, you know how much iron chloride you have. What's your stoichiometric ratio doing for you? It's allowing you to jump to one of the other compounds in your chemical equation. So I'm going to start out with my 2.7 moles of FeCl3, and I'm going to multiply by my stoichiometric ratio, where moles of FeCl3 are on the bottom and moles of chlorine are on the top. Again, according to my balanced chemical equation, 2 moles of iron 3 chloride are produced for every 3 moles of chlorine that are consumed. All right. So then I'm going to punch this into my calculator, and I get 4.05. What are my units on that 4.05? Moles. And specifically, we jumped into moles of Cl2. All right, and then sig figs. All right, this has 2 over here. And again, mole ratios are always exact. They are never going to limit your sig figs. So my final answer here would be 4.1 moles of Cl2. Cool? All right. Okay, so now let's roll everything we've been doing together here. All right. Actually, before we move on, let's just look. What category of reaction would this one be? So I got multiple reactants coming together to form that one product. This would be a synthesis reaction. Cool. All right. Let's do one more here. So when aluminum oxide is heated, it breaks apart into aluminum and oxygen. All right, so if 0.76 moles of aluminum oxide are heated, how many moles of aluminum are produced? Okay, so in this big ugly problem here, step 1 is going to be to turn this reaction description into a balanced chemical equation. Okay, then we can use that balanced chemical equation to do our math here. Oh, I guess I'm going to tell you. Aluminum oxide is a solid. So when solid aluminum oxide is heated, we want to be able to draw our complete chemical equation. Alright, so double check that your chemical equation's correct. Aluminum oxide is Al2O3. So here's my balanced chemical equation. What type of reaction would this be? So this would be a decomposition, and honestly, we don't say breaks apart, we would say decomposes, but I wasn't trying to give it away. Alright, but yes, this is a decomposition reaction. Okay, so I'm going to build my stoichiometric ratio. I'm jumping from aluminum oxide into aluminum, so that's what I'm going to build my stoichiometric ratio for. I need moles of Al2O3 on the bottom so that they cancel out and leave me with moles aluminum. And my ratio here is 3 to 1. What's up? Wait, what? Oh. Oh my gosh, I'm sorry. Blanked out over there. Oh, my bad. I was paying attention to the wrong subscripts. Okay. Yes, absolutely. So, my oxygens. Okay, thank you. My oxygens, I got to balance with a 3 out front here and a 2 there. So now I need 4 aluminums. Okay, cool. So then my stoichiometric ratio, now going back to my chemical equation, boom, moles of aluminum. Cool. So now I have 2 to 4, and let's punch this in. All right, 1.52 moles of aluminum. And then lastly, my sig figs. My initial measurement has 2. And my mole ratio is exact. So, boom. Round that off to 2 sig figs, 1.5 moles of aluminum. Thank you. It's just testing who's paying attention. Appreciate it. Cool? All right, so again, we talked about turning these descriptions of reactions into our balanced chemical equations. We talked about balancing chemical equations before, but now we're introducing this states of matter that you have to include as well. All right? And then from our balanced chemical equation, we can build these stoichiometric ratios. And these are going to be key to the math of our chemical reactions. Okay? You can see that these stoichiometric ratios are in units of what? Moles, all right? And again, that's why chemists love moles, okay? Because that's how we talk about chemical reactions. How much reactant gets consumed, how much product gets produced, all in moles, because that's the information that we get from our balanced chemical equation, okay? Now, unfortunately, there's no such thing as a mole counting machine, so practically speaking, we would use something like grams or volume, and for that, we'll have to do a little bit more work, and that is what we'll work on next time, okay? Cool.